Okay, welcome back. A hydrate is a salt that absorbs water. It incorporates water into its crystal structure. Sometimes the salt is so good at absorbing water that it absorbs so much water that it switches from being a salt with water in it to being a water with salt in it. It turns into a gooey mess on the lab bench. Not all of them, though. That's fairly rare. But when you have water incorporated into a crystal structure, that's called a hydrated crystal. I mean, it'll just absorb water from the air if there's any water from the air. So barium chloride plus water, it will have 2 molecules of water for every unit, for every formula unit of barium chloride. Okay, so that's written here as barium chloride dot 2H2O. Okay, so that's saying that for every unit of BaCl2, remember it's a salt, so there's no molecules. This is just a ratio. For every unit of BaCl2, there's 2 waters. So you can think of it as sort of extending the ratio. For every barium ion, there are 2 chlorine ions and 2 water molecules. Similarly, for magnesium sulfate, you have 1 magnesium ion for every 1 sulfate ion for every 7 molecules of water. Magnesium sulfate is very good at pulling water out of the air. Now, the question is, how do you name them? That's actually fairly straightforward. You just name the ionic compound as water, and then you use the prefixes from the covalent compounds to say how many waters are in the compound. So if there's 2 waters, it's a dihydrate. If there's 7, it's heptahydrate. If there's 1 water, monohydrate, right? So here we have copper bound to sulfate. So it's copper sulfate, right? No. Copper can take multiple charges. Okay? So we're going to have to copper sulfate. Okay. Sulfate takes a 2 minus charge. So if it's a 1-to-1 ratio, what charge does copper have to take? Well, in order to make it neutral, copper must be 2+. So it's copper 2 sulfate, and it's bound to 5 waters, so copper 2 sulfate pentahydrate. Here we have strontium bound to nitrate. Strontium is an alkaline earth metal. It only ever takes a 2+ charge, so you don't need the Roman numeral. So it's strontium nitrate, then you have 4 waters, so tetrahydrate. Okay. Now, there's no way for you guys to predict hydration, how many water molecules. So all I can do is give you the name or the formula and expect you to get the other one. You cannot get how many waters are going to go in there. So just knowing that a crystal will be hydrated doesn't give you the number of waters in the hydrated crystal. Okay. So that is what I expect for hydrates. It's not too bad. It's just another level of complication, but it's something you need to know. Hydrated crystals are fairly common, and they actually show up in lab fairly frequently because we often need to store chemicals away from water. So we will use, for example, magnesium sulfate. We'll just put down a bed of magnesium sulfate chips, and then you put down a screen on top of that. Then you put your jar of chemicals on top of that. Then you close the jar, the jar with all this stuff in it, the jar with the magnesium sulfate and the jar of chemicals in it. And then the magnesium sulfate, any water that's in there, it will absorb. And they use magnesium sulfate in particular because it turns from a light blue color when it's dry to a bright pink color when it is hydrated. So that lets you know when it's exhausted and you need to replace it. And then what you do is you just put the magnesium sulfate in the oven for a couple hours, and that'll drive all the water out. But it's very useful, and they use it all the time in labs. Now, so this is where we're going to start playing around with math. Math is a thing we have to do, and now it's going to start showing up. Okay, so remember, for ionic compounds, we are looking at the chemical formula, which is the ratio, the reduced ratio of the relationship, the ratio of the ions to one another, cations and anions. Okay? For a covalent compound, the chemical formula is not reduced. You have to show all the atoms because it's not a ratio. It's actual connections between individual atoms. Okay? This is a formula representing a ratio. This is a formula representing an actual individual molecule. Okay? But there is a thing called an empirical formula. Empirical formula is the reduced version of the covalent compound because especially back in olden days, the way to determine the formula of something was to burn it. Which might sound inefficient, but it actually works fairly well. But after you've burned it, you get a bunch of different products, and those different products will tell you what was in the original thing and in what ratio. But it won't tell you the actual amount of each thing in the original compound. So that gets you the empirical formula, the reduced version. So here we have acetylene, C2H2. The empirical formula is CH, okay? Just the reduced ratio. The reason it's called the empirical formula is because when you determine something in a lab, it's been determined empirically or experimentally. Okay. So if you have the empirical formula of something and you have the molecular mass of the thing, you can determine molecular mass using a different experiment. Then with those two things, you can find the actual formula of the compound. Okay. So, for example, here we have CH2O. That's the empirical formula. And here we have the molecular mass of the compound, 180.1. So from there, we need to find, excuse me, we need to find the actual chemical formula or molecular formula. So first, from the empirical formula, you have to get to the empirical mass. So that's just the molar mass, but for this reduced formula. Okay, so 12.01 for carbon, 1.008 times 2 for hydrogen, and 16.00 for oxygen. Boom, 30.02. So that is our empirical mass. Okay, 30.02 grams per mole. That's a G. So now we need to combine the molecular mass and the empirical mass. Sorry, that's 3. Doesn't really matter. Whatever. All right. So the molecular mass is 180.1 grams per mole. Okay. Molecular mass is just the molar mass for a molecular substance. Okay. Same thing. And the way you get the molecular formula is you're going to divide the molecular mass by the empirical mass. So 180.1 divided by 30.03 is about 6. So that means that whatever our final formula is, there are 6 of our empirical formulas in there. So what you do is you just take your empirical formula and multiply it by 6. Okay? So the invisible 1 becomes 6, 2 becomes 12, and 1 becomes 6. So for CH2O, the empirical formula was the empirical formula is CH2O, and the molecular formula is C6H12O6 because there are 6 of these inside there. Now, you can go from the empirical determination, or the percent composition, to empirical formula. So, percent composition, give me just a moment, would look something like this. This is our percent composition. Okay, so if we have a compound with carbon and and oxygen in it. We'll just start with something that only has 2. And our carbon is 27.29%, and our oxygen is 72.71%, okay, by mass. And that is what percent composition means. All right. So, given that, how can we find our empirical formula? Well, first you just assume, hey, I have 100 grams of this stuff. Well, 100 grams, 27.29% of 100 grams is 27.29 grams. And 72.71% of 100 grams is 72.71 grams. Straightforward. Okay. The next thing we're going to do is convert to moles. Okay, moles are a big deal. Okay, so moles. So you need to divide by the atomic mass, okay, the molar mass for each atom. So divide by 12.01 grams per mole. Divide by, now, once again, this could trip you up. Oxygen is a diatomic element, but we're not looking at a molecule of oxygen. We're looking at atoms of oxygen bound to something else, in this case carbon. So you have to use the atomic mass of oxygen. Okay, and when you do that, you get 2.272 moles and 4.544 moles. Okay. So now that we have moles, we can find the ratio between the atoms. Because remember, moles are directly related to the amount of stuff, the amount of atoms. Okay. So we can convert to ratio by just dividing by the smallest number. So you divide by 2.272, divide by 2.272, gets you 1 and 2. So what we're looking at here is a molecule with 1 carbon for every 2 oxygens, carbon dioxide. If our mass percentages are, let's see, it's 41.35%, 10.41%, and, just a moment, 48.24%. All right, what is the empirical formula of this? All right, first thing you do, you just grams, 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 and then you convert to moles. So divide by 12.01 grams per mole, divide by 1.008 grams per mole, divide by 14.01 grams per mole. All right. Now remember, even though hydrogen and nitrogen are both diatomic elements, we use the atomic mass, not the molecular mass, for the empirical formula. Okay, so when you convert to moles, you get 3.443 10.33 and 3.443. Okay. So now what you're going to have to do is divide by the smallest number. The smallest number here is 3.443. So we divide each of them by 3.443. Now, for carbon and nitrogen, that's easy. It's 1. For hydrogen, you put it in your calculator, and you get 3. Okay. So what whatever molecule this is, it has an empirical formula of CH3N. Okay. So just a quick warning, you cannot determine the formula just by looking at the mass percentages. Because remember, mass tells you about the amount of matter locked inside the atom, but you have to convert to moles in order to get something that's directly related to the number of atoms. So hydrogen actually has more atoms here, even though it has far less mass. So be careful about that. All right. Finally, you may occasionally have to deal with fractions. Now, my two examples, they were fortunate. They didn't come up with any fractions. But if, for example, after converting to moles and then dividing by the smallest number, you could have come up with something like 1, 2, 2.5, 1.25. Okay. Learn to recognize fractions. This means half. This means 1/4. You might see a 0.33 representing a 1/3. Okay, but you shouldn't expect anything too ridiculous. It could happen. You could end up with like a 0.14 that should represent a 1/7, but I don't expect you to have fractions memorized like I do, because I'm weird. All right, so what you do to get rid of fractions is you multiply all of them, okay, by the denominator, right? So you're going to have to multiply everything by 4. Now the 4 will take care of the 2, so you don't have to worry about that. So you multiply it all by 4, you get 4, 8, 10, and 5. And that is your empirical formula. Okay? So this particular one would be C4, H8, in 10O5, which frankly is an absurd compound. I don't think it would ever exist. But you could also get something like CHNO 1, 2, 1.33, 1.5. Okay, so this is a third and this is a half. Okay, there's no common denominator there, so you're going to have to multiply by 3 and by 2. In other words, multiply by 6 if you want to get rid of both of those fractions. And the result of that would be 6, 12, 8, and 9. Okay. So that particular one would be C6, H12, N8, O9. Now, I will try not to give you anything with multiple fractions like this, but it could happen. I'm not perfect. So be on the lookout for those sorts of common fractions. Oh, and if there are any other fractions, rounding errors, you might end up with 1.01 or 2.99. Those you would just round off. All right, and that does it for this particular presentation. So that will do it for this little lecture series. And I will meet you again in our next lecture when we begin a different set of slides.